This video will take us through the complete process of graphing transformations of a parent function. In particular, we'll focus on the type in which there is no more than one transformation on the inside of the function, but perhaps multiple transformations on the outside. The first thing you have to do is identify all of what's going on with the function you want to graph. What's the parent function? Are the transformations on the inside or the outside? Meaning, are the transformations happening horizontally or vertically? What type of transformations do you have? And what is the order of those transformations? Keeping in mind, of course, that inside always does the opposite of what you would think. This page organizes all of these ideas. You can pause the video at this point in order to copy this into your notes. Here then is the overall process I suggest for graphing your function with transformations. First, identify the parent function, transformations, and order as shown on the previous page. Second, make a quick sketch of the overall graph. What's the big picture of what's happening? I call this the macro changes. If you have any stretches or compressions, the third thing I suggest is to make a quick sketch of the feel, which we learned about for each of the parent functions, and then apply those stretches or compressions to that picture. Our feel for each parent function is based off of a reference point, so the fourth step is to consider what happens to each individual point, what I call the micro changes, and put the reference point through those micro changes. The fifth step is to then put all of these parts together, 2, 3, and 4, to graph the rest of the points using the feel from the reference point. Of course, once you've done that, you also need to check yourself. If you have a graphing calculator, you can graph the function and use the trace feature to check your points. If you are not allowed to use a graphing calculator, you of course can just plug in points to your function and see if they match your graph. Again, you can pause the video if you want to copy this down. Let's now take a look at an example. Given g of t equals 1/2 times the quantity t minus 3 cubed, all minus 4, we want to identify the parent function, sometimes called the common function, and call it f. And then we want to write g in terms of f. And finally, we want to graph g. Hopefully you can see that the parent function f is the cube function, so we can write that f of t is equal to t cubed. Writing g in terms of f means to show the relationship of g to f based on what's inside the parent function and what's outside. For this example, we get g of t is equal to 1/2 times f of t minus 3, all minus 4, since the t minus 3 appears inside the cube function, and the multiplication by 1/2 and the subtracting 4 happen outside the cube function. We're now ready to use this overall process in order to get the graph of g. First thing we have to do is identify the parent function and the transformations. We've already identified the parent function, so now to get the transformations, I actually like to point at each of the algebraic manipulations and tell myself what each of those is going to do. The 1/2 is on the outside, it's multiplication. Outside affects a graph vertically. Multiplication is a stretch or compress, and we know that outside sort of does what we'd expect, so it's actually going to compress the graph vertically. The minus 3 is on the inside of the cube function. We know that inside is a horizontal change, addition and subtraction is a shift, but inside does the opposite of what we would think, so that is actually going to shift our graph to the right 3 units. Finally, we have that subtraction of 4. It's on the outside of the cube function. Outside is a vertical change. Addition and subtraction again is a shift. But on the outside it sort of does what you would expect, and therefore that is a shift down 4 units. The final piece then of our first step in the overall process is to figure out the order of these transformations. There's only one transformation on the inside. Inside and outside transformations don't affect each other, so technically I could shift that to the right at any point I want, but I like to do my inside transformations first. It's kind of like doing parentheses first when you're thinking about order of operations. Now on the outside of the function I actually have 2 transformations, and what we have seen is that when you have more than one transformation on the outside, you should use order of operations. Therefore the multiplication is going to happen next, and finally we will take care of the subtraction. The second step in our overall process is to make a quick sketch, what I call the macro changes. This is a really rough sketch. I will just take care of this off to the side here. So I begin with my parent function. I know that my parent function is the cube function, has that little flat part in the middle, and looks basically like this. My first transformation then wants me to shift that to the right 3. So my graph will move over to the right 3. The second thing I want to do is to compress that vertically. Remember that stretches and compressions happen around the x-axis, so this x-intercept is going to stay locked, but then I'm going to compress this down here towards the x-axis, and I'm going to compress this up towards the x-axis and get a graph that's a little bit flatter for a little bit longer in the middle there, and takes a little bit longer before it goes off to infinity and negative infinity. And then finally I need to shift that graph down 4, so I have that flat part down there and then the overall shape like this. So that's the macro picture, that's the overall effect of what's happening. 1, we shifted it to the right 3. 2, we compressed it vertically. 3, we shifted it down 4 units. The third step is to draw any changes to the feel that we have learned for the parent function because of any stretches or compressions. So for the cube function, we know that the feel was starting from that flat place on the graph. You would go over 1 and up 1. You would go over 2 and up 8. Also, you would go back 1 and down 1. And you would go back 2 and down 8. In this function, we know that we are going to compress the graph vertically, so I'm going to go ahead and just take care of that by multiplying these by a half. In the y direction, instead of going up 1, I'm going to go up a half. Instead of going up 8, I'm going to go up 4. This is going to be useful later once we get the reference point set. This is going to tell us exactly how to move from that reference point to get the rest of the points that we want for our graph. The next piece is to consider what's going to happen to each individual point so that we'll know how to change the reference point. I call these micro changes. So if the macro change is to shift to the right 3, what that actually does is it adds 3 to each x coordinate. If we want to compress vertically, that actually multiplies each y coordinate by 1/2, and shifting down 4 subtracts 4 from each y coordinate. So if I go through and think about my reference point for the cube function, which is 0, 0, Shifting down 3, or in other words adding 3 to each x coordinate, will then change that to the point 3, 0. Then I'm going to compress vertically, or in other words multiply the y coordinate by a half. But of course a half times 0 is still 0. And finally, I'm going to shift down 4, or in other words subtract 4 from the y coordinate, which will give me 3, -4. I probably could have already guessed that right here in my macro picture, but just in case I wasn't exactly sure, that's what going through these micro changes will help me to do. I now know where the reference point is that I'm going to start this whole graph from. I'm ready now to put all of this together, to look at the big picture, the macro changes, the overall graph, which I saw here in my quick sketch, to put that together with the changes that are going to happen because of stretches and compressions to that feel that I already know for the parent function, and starting from the reference point that has been transformed based on those micro changes. Put all of that together now in order to draw the graph. You'll notice that one of the important things from the macro picture here that's helpful is it kind of tells me where I want to set up my axes. I see that I want a lot of things in the fourth quadrant here, the fourth quadrant, and so there's really no need of putting my axes right smack dab in the middle of my grid. So I'm going to set up my axes in a very smart way because of that macro picture that I've already drawn. I will begin by first marking my scale so that it's very clear how I'm going to use my grid. Skipping ahead gives me this. So next I'm going to set that reference point. After putting it through the micro changes, we saw that it is going to be at 3, -4. From there, I want to get the rest of my points based off of this feel, which says that if I go left or right by 1, I'm going to go down and up by a half, etc. So if I go to the right one, I'm going to go up a half. If I go to the left one, I'm going to go down a half. It also says that if I were to move 2 over left or right from my reference point, I'm going to go up and down 4. So moving 2, I'm going to go up 4, which by the way would be an x-intercept. And moving to the left 2, I'm going to go down 4, putting me at -8. So this is really the reason that we wanted to learn the feel. After taking care of my stretches and compressions, and after setting my reference point, I can get the rest of the graph very quickly and easily by using that feel. I'm now ready to draw in my graph. Remember that reference point is where the graph of the cube function is flat. That's about a tangent line, or what I've been calling headlights. They should be perfectly parallel with the x-axis. From there we're going to draw up and away. On the other side we're going to draw down and away through the points we have. Just need to label some points. This is at 1, -8. This one is at 2. And then a half down from -4 would be -9/2. Remember to always give me fractions. This point we already said was at 3, -4. This point is at 4, and then a half up from the -4 is -7/2. And finally I have this x-intercept at 5, 0. So of course at this point I should check myself. If I have a graphing calculator, I could just plug that in and check the points. If I'm not allowed to use a graphing calculator, I just want to plug in some of those x coordinates. Plugging in a 1, I get 1/2 times 1 minus 3 cubed minus 4. That gives me a half of -2 cubed minus 4, which is a half of -8 minus 4, or in other words, -4 minus 4 equal to -8. as I saw on my graph.